Section: Introduction. In this section, we discuss the role of large language models, LLMs, as essential tools for tackling complex tasks in interactive environments. We observe that LLM-based agents are increasingly used for tasks that require autonomous decision-making, error correction, and task optimization. However, we note that existing methods face limitations due to their dependence on behavior cloning from expert models. This reliance on perfect trajectories for training hinders the agent's ability to self-correct errors, which can lead to a series of failures and less effective task performance. We recognize that previous approaches have attempted to use explicit error signals or reward functions for self-correction, but these methods often focus on single-turn tasks and do not provide clear error signals until the end of a task. In contrast, many tasks in interactive environments involve multiple interactions and do not reveal errors until the final outcome. Additionally, creating effective reward functions for assessing intermediate actions in lengthy interactions is challenging. A significant barrier to improving error recovery in these environments is the lack of detailed reflection data at each step. Traditional methods for gathering this data are labor-intensive and costly, making it difficult for models to learn from their mistakes. Therefore, we emphasize the importance of building reflection datasets to help agents develop self-reflection and better decision-making skills. However, automatically creating these training samples is complex. We highlight that timely revisions are crucial. If corrections are only made at the end of a task, agents miss the opportunity to learn from errors as they happen. This delay can lead to serious mistakes, especially if they occur early in the process. To tackle these issues, we introduce Agent R, a new framework that allows LLM-based agents to reflect and improve in real time. Unlike previous methods that focus solely on the correctness of outcomes, Agent R employs a dynamic self-training approach that corrects errors at each step. By using Monte Carlo tree search, MCTS, Agent R creates training samples that help recover correct paths from incorrect ones, guiding agents through complex decision-making. Specifically, it identifies the best point to revise an incorrect trajectory and connects it to the correct path, allowing for immediate recovery rather than waiting until the end. This process enhances the agent's ability to reflect and reduces the risk of creating inconsistent trajectories. To further improve Agent R, we refine its error correction and dataset construction iteratively, enabling the agent to enhance its performance continuously. Our experiments across 3 different interactive environments show that Agent R significantly outperforms existing methods, providing language agents with self-correction abilities akin to human decision-making. Notably, training with revised trajectories is more effective than using expert trajectories, allowing agents to better identify and correct mistakes while avoiding repetitive errors. In summary, we are the first to address the critical challenge of error correction in interactive environments for language agents, a gap overlooked by previous methods. We present Agent R, an innovative iterative framework that equips language agents with self-reflection capabilities. By utilizing MCTS and a model-guided reflection mechanism, Agent R dynamically constructs and revises trajectories, enabling agents to autonomously improve their behavior without relying on human supervision. Our extensive experiments demonstrate that Agent R significantly enhances performance, allowing agents to detect and address errors in real time while managing long-term tasks more effectively. Section Summary. In this section, we discuss the limitations of current LLM-based agents in interactive environments, particularly their inability to self-correct errors in real time due to reliance on expert trajectories. We introduce Agent R, a novel framework that enables dynamic error revision and self-reflection, significantly improving the agent's performance in complex decision-making tasks by allowing them to autonomously identify and correct mistakes as they occur. Section: Monte Carlo tree search. In this section, we discuss Monte Carlo tree search, MCTS, a decision-making algorithm that helps us navigate complex choices. MCTS builds a search tree and simulates outcomes to evaluate different actions. It works through 4 main stages. 1. Selection. We choose the next node to expand using a strategy called Upper Confidence Bound for Trees, UCT. 2. Expansion. We generate new nodes based on the selected node and add them to the tree. 3. Simulation. We run multiple simulations from the new node to either a terminal state or a set maximum depth. 4. Backpropagation. We update the values of the nodes based on the simulation results. Next, we introduce Agent R, which has two main phases. Phase 1 involves model-guided reflection trajectory generation, where we use MCTS to create revision trajectories that turn incorrect paths into correct ones by finding the best reflection step for the current policy model. Phase 2 is iterative self-training with revision trajectories, where we train agents on these dynamically created revision paths. This iterative approach allows agents to learn progressively more challenging revision steps, enhancing their decision-making and preventing repeated errors. We define 4 types of trajectories essential to Agent R: initial trajectory, the starting sequence of actions and observations. Bad trajectory, an extension of the initial trajectory that includes suboptimal actions, leading to poor outcomes. Good trajectory, a path that builds on the initial trajectory with optimal actions, resulting in better rewards. Revision trajectory, created by correcting a bad trajectory with a good one, marked by a transition point and a brief reflection signal that prompts the agent to consider its past actions. The final reward from the environment helps us set constraints to ensure bad trajectories can be effectively improved into good ones, maintaining high quality in the revision trajectories. To gather revision trajectories, we utilize MCTS to explore and reflect on errors in the trajectory space. Starting from the initial root node, MCTS goes through the 4 stages of selection, expansion, simulation, and backpropagation. During simulation, we use a default policy to sample future actions, performing multiple rollouts to enhance reward estimation and ensure diverse trajectories. In the selection phase, we balance exploration and exploitation using the UCT criterion. When we reach a terminal node, we generate a trajectory from the root to the terminal node and receive the final reward from the environment. Good and bad trajectories share the same initial path but diverge based on the quality determined by the final reward. To create revision trajectories, we manually design 10 different revision thoughts and randomly select one to connect the bad and good trajectory segments. We also introduce a simple method called the direct revision trajectory, where the good trajectory is directly added to the end of the bad trajectory. However, this method overlooks the importance of timely revisions, which are crucial for effective agent learning and error detection throughout the trajectory. Section Summary. In this section, we detail Agent R, which employs Monte Carlo tree search, MCTS, to generate revision trajectories that correct errors in decision-making processes through 2 phases: model-guided reflection and iterative self-training. We define various trajectory types and emphasize the importance of timely revisions to enhance the agent's learning and decision-making capabilities, avoiding cascading errors. Section: Transition Point Determination with Actor Model. In this section, we propose a method for determining transition points using a model-guided approach inspired by human thinking. Our language agent assesses its own actions within poorly performing trajectories to spot mistakes based on its current abilities. When the agent identifies an incorrect action, it marks the transition point and cuts off the bad trajectory there. It then creates a new trajectory by merging the corrected part of the bad trajectory with the corresponding part of a successful trajectory. This method is interactive and relies on the agent's self-awareness to improve its actions in real time. Our experiments show that this transition point determination is more effective than simply revising actions directly. The prompt for this process is detailed in the appendix, ensuring that revisions are based on the agent's learned experiences, which helps it improve from weaker to stronger behaviors. In the second phase, we focus on training language agents using the revision trajectories generated through Monte Carlo tree search, MCTS. The agent learns to identify and fix errors dynamically through self-reflection, enhancing its policy based on its experiences. While training on these revision trajectories helps develop self-reflection, it can initially limit the agent's ability to find the right path. Previous methods often used both optimal and revision trajectories, but this still faced the cold start issue, where the agent starts with little knowledge and relies on trial and error, leading to few optimal paths early on. To tackle this, we suggest mixing revision trajectories with successful ones during training. As we progress through self-training, we gradually increase a specific value to encourage good trajectories to align more closely with optimal ones. This helps the agent improve its error reflection and trajectory identification over time. Additionally, we combine our agent's trajectory data with general datasets, like Shared GPT, to enhance its ability to generalize across different environments. For our base model, we aim to find the best policy that minimizes a loss function, which incorporates input-output pairs from the general dataset and a mixture ratio. To ensure stability, we continuously refine our error correction and dataset construction processes. In each iteration, we recollect model-guided revision trajectories and optimize our approach. As the agent trains through multiple iterations, it develops better self-reflection and shifts from weaker, error-prone behaviors to stronger, more effective performance in interactive settings. This process allows the agent to recover from mistakes and learn from its experiences, enhancing its overall performance. We conduct extensive experiments in 3 interactive environments to validate the effectiveness of our approach. These environments include WebShop, an online shopping platform with numerous products, Science World, which tests scientific reasoning through various tasks, and TextCraft, where agents craft items based on Minecraft recipes. Our experiments take place on Agent Gym, a platform with various agent environments. We create revision trajectories by sampling simulations from each environment, setting a distinguishable gap between bad and good trajectories. To address the cold start problem, we start with a low threshold for good trajectories, which we gradually increase in later iterations. We run our method for 3 iterations, adjusting the thresholds accordingly. By the 3rd iteration, the good trajectories align closely with optimal ones. Following established methods, we use Shared GPT as our general dataset and select specific tasks for testing in each environment. Section Summary. In this section, we propose a model-guided approach for determining transition points in language agents' trajectories, allowing them to self-correct errors and improve their performance through iterative self-training with a mix of revision and good trajectories. Our experiments across 3 interactive environments demonstrate the effectiveness of this method in enhancing the agent's self-reflection and error recovery capabilities. Section: MCTS Settings. In this section, we outline our settings for Monte Carlo Tree Search, MCTS, and training. For our simulations across 3 interactive environments, we generate 63 rollouts for each Monte Carlo estimation, with a depth of 20 for all tasks. During the expansion phase, we set the temperature of the language models to 1, and at each depth, the models produce 4 candidate actions as new child nodes. To balance exploration and exploitation in the selection phase, we adjust the UCT parameter accordingly. For training, we run Agent R for 3 iterations, presenting results from the 3rd iteration. We set the number of epochs to 3 for the first iteration and 1 for the others to prevent overfitting. Our main model is the Instruct version of LLAMA 3.1 to 8b. In terms of baselines, we include closed-source models like GPT 3.5 Turbo and GPT 4o, as well as open-source models like Llama 2 Chat and agents trained on expert trajectories, such as Agent LM and Agent Flan. We also compare our method, ETO, which first applies supervised fine-tuning to a base agent and then fine-tunes it with pairs of good and bad trajectories. Additionally, we report results for LLAMA 3.1 to 8b Instruct trained on a mix of direct revision and good trajectories. For evaluation metrics, we use the average final reward for SciWorld and WebShop, while for TextCraft, we measure the success rate. The maximum number of rounds is capped at 100 across all environments. Our main results indicate that Agent R significantly enhances the performance of language agents in interactive settings, outperforming advanced closed-source models and agents trained on expert data. This underscores the importance of revising incorrect trajectories during learning rather than relying solely on expert data. The trajectories created by Agent R, through self-reflection and early error detection, lead to quicker recovery and more stable learning, preventing error propagation and resulting in higher quality models. We also find that training with Agent R trajectories can surpass using optimal trajectories. We compare our approach with Llama-3.1-8b and Struct trained on direct revision trajectories and other variants. The results show that iterative supervised fine-tuning with Agent R trajectories gradually improves the model's capabilities, highlighting the value of mixing revision trajectories with optimal ones for better performance. However, adding only good trajectories can reduce performance due to potential noise, while revision trajectories provide valuable error recovery information. Furthermore, we explore how Agent R equips language agents with self-reflection capabilities. We analyze failure trajectories from the test set of LLAMA 3.1 to 8b and Struct and evaluate whether agents can correct these failures after truncating the trajectories. Our findings reveal that training with Agent R revision trajectories outperforms direct revision methods, emphasizing the need for early reflection during the trajectory. While training on expert trajectories can enhance performance, it lacks adequate self-reflection capabilities, which are crucial for timely error correction. Although GPT-4o shows better self-reflection than some other models, it still performs worse than Agent LM and Agent Evil on the test set. Section Summary. In this section, we detail our Monte Carlo tree search, MCTS, settings and training configurations for Agent R, highlighting its superior performance in interactive environments compared to both closed-source and expert-trained models. We emphasize the importance of incorporating self-reflection and error recovery in training, demonstrating that our approach leads to more effective learning and better outcomes than traditional methods. Section. Finding 3. Training with revision trajectories helps agents more easily identify and correct erroneous actions. In this section, we present our findings on the impact of training with revision trajectories on agent performance. Finding 3 highlights that training with revision trajectories enables agents to more easily spot and correct mistakes. We construct these trajectories by having agents identify the first mistake in a flawed sequence and then append the correct actions from that point onward. To assess whether agents trained with iterative supervised fine-tuning, SFT, can quickly find the first error, we measure the revision length, which is the number of actions from the start of the flawed trajectory to the first mistake. Our results show that Agent R significantly enhances the agent's ability to recognize errors, as indicated by a shorter average revision length. This suggests that integrating error correction earlier in the trajectory allows the model to adjust its actions more efficiently. Furthermore, this improvement reflects the actor model's enhanced ability to reflect, which could be beneficial for assisting other models in future research. Finding 4 reveals that training with revision trajectories helps agents avoid getting stuck in repetitive loops. We analyze the length of repeated action sequences in test trajectories under various training conditions. The average count of repeated sequences indicates how often agents get trapped in loops. For instance, if a sequence of 2 actions is repeated 5 times on average, it shows a tendency to loop. Our findings indicate that while agents can achieve optimal trajectories through Monte Carlo tree search, MCTS, these paths may include repeated or irrelevant actions that lead to dead loops, harming performance. In contrast, training with Agent R's trajectories significantly reduces these dead loops, suggesting that agents trained this way are more inclined to explore new actions and avoid local traps. This underscores the value of revision trajectories in promoting exploration and improving overall performance. Finding 5 demonstrates that multitask training is a more effective strategy for Agent R. We compare our multitask approach with single-task training, where we gather good and revised trajectories separately for each task. The results indicate that multitask training is superior for training language agents in interactive settings. Additionally, the trajectories collected by Agent R are particularly well suited for this approach, further boosting performance. Detailed results from 3 environments and additional analysis can be found in the appendix. We also discuss agent learning in interactive environments, which can be categorized into 3 strategies. 1. The prompt-based strategy, which uses human-written prompts to guide language models in summarizing experiences and enhancing their knowledge. 2. The inference time search strategy, which employs search algorithms like tree of thought and MCTS to find optimal trajectories during inference, utilizing prior knowledge for efficiency. 3. The training-based strategy, which uses supervised fine-tuning or direct preference optimization to train language models, with data collected from expert models or generated through exploration. Lastly, we address self-correction in large language models, LLMs. While self-correction is a valuable capability, current LLMs often struggle with it. Some studies rely on prompt engineering but fail to achieve significant self-correction and may even degrade performance. To tackle these challenges, various approaches suggest collecting revision data from human annotators or expert models, but these methods typically focus on specific tasks with clear error signals. Our paper explores self-correction in interactive environments where agents do not have explicit error signals and must rely on their observations.